This presentation by Tom Gallagher follows on from his first lecture on paleoclimatology and focuses on more modern times. Because of COVID-19, Tom joins us via Zoom.
We're going to go ahead and do a quick review of what we covered in part one. And then we'll move off into the current historical period where we want to discuss a lot about the Holocene. Now that's the last 11,000 years to right up to the recent. The global ocean currents of today will be stressed within that. And the other portion, which is very important, is the atmosphere. The atmosphere is going to be discussed with all of its estimations and energy errors. We want to go ahead and talk about the radiation budget of that. What we will do in subsequent part three, we'll be trying to discuss the uncertainty that's generated in all of these estimates by the clouds, the ozone, and of course, we wanted to finish off with the positive biosystems that are being generated by CO2. In part one, to recap that, we used the solar energy, of course, and the Milankovitch cycles that control that with the Earth-Sun system. We looked at the solar controls on energy of that system, and that the oceans control the energy storage in the system and amplify it. The water, in all of its phases, drives the energy cycle of climate. Continental drift was added as another layer, which certainly makes a big difference in the amount of energy that can be stored. The CO2 and temperature, we concluded from all of this detailed fossil evidence and data on CO2 and temperature do not correlate. CO2 is controlled by volcanic and oceanic sourcing, and temperature is being controlled by the sun, the oceans, and the continents drifting, creating open or closed continental areas, oceanic areas, excuse me. The default condition that we are in now is cold, dry, dusty, and glacial. What has happened in the past, where we had very warm periods like the Eocene, where it was warm, wet, and non-glacial. No glaciers existed. Vegetation and civilization prospered during those warmer, wetter times. This is a picture that we used last time to illustrate the circumpolar and the circumequatorial current systems that existed during the Eocene. This is a simplified version thereof and looks at the warmer, wetter, and more tropical world of the Eocene before the southern oceans opened and the equatorial passages for those currents that were going around the equator closed. Thus, after that point of closing of the equatorial currents, we got into a colder, drier, more glacial world. This was the scatter plot, which illustrates CO2 versus temperature. Temperature moves in large steps in conjunction with the actual movements of these continental plates. So as the continents drifted, the Antarctic Southern Ocean opened and the Tethys Sea around the equator closed. Finally, the Panama Canal and the Indonesian Straits closed or partly closed, creating where we are today from 67 million years ago. This graph is of the past fossil temperature and CO2, and it is in strong agreement with steps, not necessarily any kind of continuum between those two end members. So the temperature corresponding to the major openings and closings is the important take-home message. And solar energy and ocean current storage of that energy governs the temperature. The greenhouse gas theory and CO2 are completely absent from this view of history. The Antarctic core and temperature data in this illustration are made from oxygen isotope work and show the thermal history of the past 400,000 years. As reviewed in part 1, the warm peaks are times of Earth-Sun system coincidence where warming could take place. These, the lows, are where 100,000-year-long periods of cold took place because of the Milankovitch cycle. The last period of time, the Holocene here, at 11,000 years of Earth history, the last 11,000 years of Earth history is where we want to focus now. We're in that last little peak, and we should prepare for something to be cooling after that. In this red box, we'll do a lot of expanding and explaining of what's happening in the current period of time. This is a blow up of that 11,000 year period. The arc of proxy temperatures in the Holocene period is magnified here in the black jagged line. Note that during the warmest part, the climate optimum, the CO2 is lowest, not at all as theory would predict. It's very low CO2, high temperature. The purple arc is the tilt of the Earth on its axis, its obliquity. The temperatures were highest when the axial tilt of the Earth and the Sun was 24.3 degrees at the top. And now we are at 23.5 degrees. Carbon dioxide and methane, both plotted here, do not track the temperature and actually are anti-correlative with temperature during the last 11,000 years. We are now in the period called the Neoglacial, part of the cooling Holocene that we have just come through, and the coldest part was the Little Ice Age here. The Holocene reconstruction of solar activity based on beryllium-10 records and carbon-14 records shows that the solar activity has recently recovered to above normal after dipping during the Little Ice Age, shown here. We are returning to a higher point we have been in much higher solar activity periods. The early Holocene maxima warm period shows very similar high solar activity. The only driver that can create Earth system energy is the sun. These solar indicators of fossil solar activity show significant variability. The only way to retain and store that energy from the sun is to drive it through the water cycle. This is a blow up, once again, only this time of only the last 4,000 years of human history this time. And we're dealing with Northern Hemisphere Greenland ice core. We're seeming to get a pattern, a cyclicity to this. The green line is showing you that. And the blue line is the temperatures as per the ice core. We appear to have a rhythmic and steady declining temperature. So we're declining through the whole period. And we are now, as I mentioned, in the Neoglacial. So we're moving into this, and we have the Little Ice Age period here. Period covered is very historic and shows that dynasties succeeded during the warm periods of human history, the Minoan, the Roman, the medieval, the modern periods. But there are cold, dark, and difficult times in between these good times, the Dark Ages, the Little Ice Age, etc. We have just recovered from the last low of the Little Ice Age, and which generated 400 to 600 years of glacial advances. The trend of temperatures is down for the whole period. This is a blow up of the last few years of this solar activity based on beryllium-10 anomalies, lowest during the Little Ice Age and growing toward the modern climate warm period. The sun is very active now in this area. It was very dormant through the Little Ice Age and has very few sunspots compared to the cycles of today. Each solar cycle, in red, is 11 to 12 years between peak and trough. The lower cycles, when the solar intensity and sunspots drop near zero, are those areas of cold, and the temperature falls. What we have are periods of ice age. In this particular case, accumulation of glacial ice. Here's another view of that solar activity data, the little ice age period here extending right through to this portion with a small aberration here of energy and then continuing to climb to today. Let's look at some lake core. Now this would be coring from a lake in Minnesota called Elk Lake. It's a place at the meeting point of three major climatic zones in North America: the Pacific, the Arctic, and the Gulf of Mexico. They all influence this area. In these cores, we see the thickness here represented as years of age of the core, 11,000, the beginning of the Holocene, up to today, modern. We look at the types of materials that are within those cores, from pollen of trees, from sagebrush, etc., which were found in those areas. Sagebrush is blooming here. Quartz, this would be sand deposited, is here, and sodium concentrations here. This is a dry period of time. This is a little bit different. Why such a dry period? This is also a part of that optimum period. We're in the Neoglacial. We've come out of it and moved into a different period. So optimum conditions aren't the same everywhere, all places. What you might view as optimum in this situation when you're in dry and dusty might not be what you really want. But here's a summary. This is what the globe looked like in the Holocene optimum, 10,000 to 5,500 years ago, where the climates were very different than they are today. There was drying of Elk Lake in central North America. There were humid monsoons that dominated what we now think of as large deserts in Africa and in Southeast Asia. The position of this line, the ITCZ, the Intertropical Convergence Zone, is shown on the map, and it shifts to the north, and we'll see later on to the south. This is the zone of convergence of upper level winds and lower level tropical winds on the Earth. This is what it looked like in the Neoglacial, or does in the Neoglacial, where we are now. The ITCZ has moved south. Dry has been replaced by humid in central North America. These are the kinds of changes that takes place over 11,000 years of climate variation within what we see as the warm period that we're in right now. On this slide, we're showing something called albedo. Albedo is a reflectivity off of the surfaces and the materials on the Earth's surface. What we're seeing here are forests and vegetation that have low albedo, and water does too, but water's the lowest. It's very important that we concentrate on that. Highest absorption of water, of energy within the water. The most notable thing in this diagram is the water. And what we need to do is think of it as the greatest absorber of solar radiation energy, especially of the high energy bands of radiation in the ultraviolet, the shortest wavelengths of solar radiation. This is the major reason why solar and water systems drive climate. It's the absorption by something that covers more than 70% of the Earth's surface, the water, that makes all the difference. Why is it so different? Water versus air. This would be the cooling rate that you would experience from those two equal amounts. And this is what we're talking about in terms of the inability of air and the atmosphere to make the whole difference. Energy in the form of water and water vapor are what we really want to stress now. The energy storage systems are so strikingly different between air and the ocean that it's hardly even possible to illustrate them at all. But what we do know is the Gulf Stream distribution system, shown here on the right, is the reason why Europe remains so warm, even though it is at a latitude of northern Canada or northern Russia. It's basking in the glow of the retained energy of the ocean system, the Gulf Stream. In a polar vortex-dominated North American winter, we look like this. This is the cold polar vortex, extremely cold, -30 to -50 in this area. And the temperature is very obviously being shielded and modified by the oceans which surround us. So the role of the ocean in heat storage and climate is just now, however, starting to be properly documented. Climate models have still not properly realized the storage and redistribution of energy from this climate and weather driver. Very few can claim to understand and document the real changes due to the oceans at all their depth levels. The planet of the past had many large continuous heat accumulating ocean currents, as we remember from part 1. Today, we have some of these large climate creators still around. The most significant is the oscillating El Nino, La Nina system of the tropical Pacific Ocean. They call it the NCO. The map shows the most recent precipitation results from El Nino here in the El Nino 3.4 region. The Pacific has entered a drier, cooler La Nina phase now in 2021. Tree ring studies of very old pine trees in high levels that are in continents near and influenced by El Nino are shown here. This is one of those trees. It's a pine. It's very high up in some of the near desert conditions at altitude near El Nino. Note that the rise of strong episodes is coincident with the emergence out of the little ice age here. And these strong episodes are followed by weak ones, El Nino, La Nina. A trend line is shown in green. The modern observations are shown in red. And these are all of the tree growth recording components of the sporadic oscillating El Nino. These distorted beach ball-like pictures show the contrasting years between what is a strong El Nino here in the South Pacific and a La Nina in the South Pacific. These pulse back and forth on 2 to 7 year cycles, and the areas around them are significantly affected by large swings between the wet and the dry times. Some researchers tie these pulses to solar cycles, which have more of a 10 to 12 year frequency. Here's El Nino and rainfall and what happens wet and dry. Here's that wet component of El Nino in the Pacific. Here are the dry areas of Australia and South America beside it. Then you put in La Nina and its rainfall, and you get what is almost a perfect mirror image within the areas of the tropics. So what was wet is dry. What was dry is wet. This is the 2016 El Nino. These are the cooler periods that followed it. We're now into the 2021 El Nino, La Nina. If models are made, and they are, of this surface sea temperature prediction, what happens here? We've got a complete scatter. These are the models that have been built to try to anticipate what El Nino is going to be like in the future. This is April of 2021. The studies of the ocean current systems need a significant amount of work, as the ocean systems are said to control 90% of the heat flow imbalances of the atmospheric models. Here we have a scatter. North of El Nino, there is something which is called the Pacific decadal oscillation. more along the lines of a decade long, like the solar cycles. The Japanese current makes up a big part of that. This is a picture made by NASA in their null school on the internet. What it shows is the currents, the NCO, this would be El Nino. It shows the Gulf Stream here. It shows the Japanese current here, and the rest of the tropical and subtropical southern currents that exist within the world. Europe needs the Gulf Stream. Japan, the influence of the Japanese current. The NCO is big and very important. These are the major global heat storage engines of our current neoglacial period. Would Europe be like northern Canada or Russia without the Gulf Stream? This is the oscillation of that North Atlantic current and how it varies from warmer to colder and completely controls the European weather systems and sometimes even fish yields. The atmosphere, I'm going to call it a leaky radiating cap. I'll get to that in a little while, why I've termed it that way. It's a complex, layered composition, of course, very important to us, of gases and water and ozone and plasmas. It's preserved by the magnetosphere, a layer up higher, which is our protected zone, the zone that the magnetic field of the Earth protects us from the solar radiation in. The lower troposphere is dominated by water vapor and ocean energy, as we've discussed. The water vapor varies from 10,000 to 40,000 parts per million and is much lighter and buoyant in air, air being dominantly oxygen and nitrogen. Storing energy in its phases is what water can do and very successfully modifies the world's weather and climate as a result. Thermal inversions above the tropopause and the stratosphere and the ozone cap area are something that we'll probably have to deal with in later, but we will talk about briefly here. The atmosphere has a low thermal capacity. It operates by energy loss, dominantly, loss to space. So that's the leaky cap part of it. The CO2 present in the lower parts is not present in the form that we have been told or how we have alluded to it before. It's not pure CO2, and we'll get into that with our discussions of carbonic acid. The layers of this atmosphere are shown here by a space shuttle shot. The troposphere is that oranger zone down closer to the surface, and of course is the area that we're most concerned with. The stratosphere is above it. The ozone layer is within that stratosphere. Here's that magnetosphere, the Earth's protective shell. Because we have a magnetic field in the Earth, the lines of magnetic force control this shock wave, this bow wave, which would otherwise be highly destructive to our atmosphere. Here are those layers. And below that protective magnetic envelope, our atmosphere has formed and retained a layered structure. The yellow line shows the temperature profile of these various layers. The atmospheric pressure line is the black one on the right, and it shows a rapid loss of pressure as we rise above Mount Everest, shown there. Our life zone is the troposphere, and it's governed and dominated by water in all of its forms, ice, water, and gas. This zone lies below the tropopause, which is a strong thermal inversion, shown here near the tops of that deck of clouds down there. This thermal inversion is also the point at which ultraviolet light creates an ozone layer, which heats So this is a zone of heating again in the ozone layer. The stratospheric zone is the highest and is the beginning of the tenuous ozone layer. And that is an inversion, which of course caps that thermal loss, which we were experiencing in the troposphere. Troposphere has an adiabatic cooling rate, which is very extreme, and then things reverse. Our focus will be on these lower zones. This is another view of that critical inversion zone capping the thermal heat loss of the troposphere at the tropopause. Above that, we see the magnetosphere, and above it is the cold vacuum of space. This is a view north-south, north to south, and it's a cross-section through that lower portion, our troposphere, and shows a very unusual feature. Here at the poles, it's low, and this is the cloud deck and the tropopause here in purple. And this is the tropopause over the equator at 0 latitude. There are jet streams occupying this step, this sudden jump within the height of the tropopause. We go from 7 to 8 kilometers at the poles to get up to 17 or 18 kilometers or more at the equator. Intense jet streams, as I mentioned, are sitting in those blue areas. They inhabit the portions near the step of the bulge, and these winds are due to the interface of the thermal zones and the Coriolis forces from the rotation of the Earth. These wind systems partially isolate the polar regions from the equatorial regions, and the complete thermal regime will be a little clearer later on. This is a picture taking the world in 3 different views. This is the height of the tropopause in kilometers. This is the temperature of that tropopause. And this is the pressure of the air pressure in it. This sudden break in temperature profiles is where we are seeing that large step. At the equinox is where we're viewing this, not extreme winter or summer, but extreme winter, summer, seasonal tilts of the axis of the Earth move these zones north or south. This is a view showing upper level winds of the Earth, very high velocity winds. In these areas, 200 to 300 kilometers per hour. This is the barrier now in May of 2021 against the warming versus the cooling. So it is isolating those parts of the atmosphere. These are the portions that sit where the blue areas were in the last diagram. It's of a low pressure zone higher up in the atmosphere where these jet streams exist and dominate. So we get back to that ITCZ and the variation in it in today's world. It moves, but it's quite asymmetric. It's not equal around the equator as we might think. It moves from July here in the northern hemisphere summer to northern hemisphere winter here. Sometimes it's coincident, other times quite separate under the current conditions. This is an attempt to talk in a very capsuled way about the history of global warming theory. We still have to think about it as a theory, like a lot of other theories, and still needing a lot of proofs and a lot of further development. This slide represents the timeline of global warming theory, the greenhouse theory. From earliest times during the emergence from the Little Ice Age, back over here, the proponents during this very early period, most notably this particular fellow here, Arrhenius, published on something during a global cooling period. He was emerging in Sweden from the Little Ice Age. He published in 1896 and proposed the theory of greenhouse gas. He hoped that it would preserve the temperature of the Earth and make it warmer. Carbonic acid is what he used in his analysis, and he was right. His conjecture, his early conjecture, was about carbonic acid to extract the Earth from this cold period. And the theory was in touch with the real form of CO2 in the atmosphere, where it combines with water vapor. This is a biological atmospheric theory. Subsequent efforts to look at the theory stumbled on saturation of greenhouse gases, and the effects then of the atomic theory to analyze it and how irradiation affected these vibrating greenhouse gases. Of significant note, it took until 1933 to discover how plants actually receive and process water and CO2 by the use of this catalyst, carbonic anhydrase. Without it, we would not be able to break down the carbonic acid in the system to generate the products necessary for photosynthesis. Other discoveries, such as continental drift, have allowed us to modify how we look at climate and the drivers, as we did in part one. Only very recently have the major drivers of climate change and temperature become evident in the inclusion of proper solar information. We've also got to include the ocean involvement. We've got to include the ozone layer. And lastly, the contribution of clouds and cosmic radiation. These might have to be part of a third talk. So this might be a way of looking at the abundance and temperature regulating components of the gases in the atmosphere, the two major ones: water vapor, which is dominant and lighter than the other gases. It falls off with elevation, however. It is topped out at the freezing point in the high clouds, like the cirrus clouds shown here. In the lower troposphere, CO2 is tied up as carbonic acid and water in the water vapor, and it rises with it, separating in the upper atmosphere at the freezing point. The dynamics of real atmosphere and CO2 needs to be better understood. Let's have a closer look. This was the original paper of Arrhenius. Greenhouse gas theory. It involved carbonic acid, not CO2, but for good reasons. In this paper, he knew about biochemistry of CO2 and water. He used these to actually support his theory. He was living in Sweden, and it was pretty cold. We have strayed further from the path of real data and science that Arrhenius might have been trying to look at. We have generated models. They have not done very well. This illustrates the upper tropospheric results predicted versus the hard facts shown by balloons and satellites, etc. The only model of this group of 102 to even come close to reality is in this atmospheric level was conducted by a group of Russian scientists. These are all those other ones as an average of them, all this scatter. These are the actual results from balloon and satellite data sets. This is all in very real time. This period here, 1995, is about where we start to depart from reality with the models. Why do we still use these projections for our political planning purposes? Let's look at some major problems and techniques of computer predictive modeling. This is a complex cartoon, often forming the basis for atmospheric temperature predictions. It is so complex that the individual parts have large estimations without data underlying them. These have error limits, but they're not stated. Most models do not properly lay out these error limits. Any good experiment or research paper must do so. This illustration is an honest attempt, however, to quantify the pluses or minuses error limits of various arrows and energy flows in the atmosphere only. We're forgetting about the ocean, and we're forgetting about clouds in this particular case as well. Why are the model errors so great? Why do environmental error limits vastly exceed the resolution of the predicted outcomes, the imbalances? Let's look at some of these experimental errors. The surface imbalance here. This is 0.6 watts per square meter. It is plus or minus 17. The credibility has been lost, and many variables are being used without foundation. This is the problem of using models in a very dynamic, interactive natural system. The resolution of the answers are too small to fit within the limits of the errors that are evident in the assumptions. No graduate thesis could ever receive a passing grade if it suffered from so many errors and did not quote its limitations in numbers, its error bars. Very large natural energy systems of the ocean and the clouds are missing and incomplete in these predictions. The size of these errors in judgment and the projection of imbalances are estimated to be 90% for the ocean and up to 30% for those clouds. The physics of solar radiation in the atmosphere is what we're going to review now. These are the radiation black body curves, so-called, for energy radiation absorption. And these are relative to the sun and to the earth, solar and earth. They are on a common wavelength horizontal axis, but are grossly exaggerated in their vertical axis to fit on the chart. The Earth blackbody curve radiates very weakly in the infrared spectral area, peaking at about 10 microns of wavelength. The Sun blackbody curve is in the visible spectrum in very high energy wavelengths at about 0.5 microns. Solar variations heat and have a significant effect on the radiation budget of the Earth. The vertical power scale is totally different between the two sides, 1,000,000 to 1. The cumulative power, the area under the curves, can be also compared only with numbers. Here we see a difference of 262,500 times in the power under these two curves. Solar variations dominate the incoming high energy shortwave radiation, as do clouds, water vapor, and highly reflected snow, ice, etc. The outgoing radiation window of Earth is shown in blue, and the incoming solar radiation curve is shown here, remembering that these are vastly different in their real scale. But this gives us a chance to look at the absorption, the various substances within the air that are doing that absorbing, and the percentage of total absorption that takes place. We're dealing with the same microns across the bottom, 10 for the center of the Earth field and about 0.5 for the center of the sun. We'll call these fields the Earth glow and the solar glow over here. We have various lines here which are showing different temperatures. As we rise up in the atmosphere, we have to consider different areas of temperature which the Earth's atmosphere has. These are in degrees Kelvin. The major active gases are going to be discussed. We're going to be looking at also the positions of each one of these peaks. These are the peaks in water. These are of carbon dioxide, very spiky and localized. This is one which we'll concentrate on a lot here at 15 microns. This is what happens to the energy as we move across this same diagram. Energy falls drastically across the diagram here in electron volts of oscillating energy. These are the electronic components of energy absorption, vibrational, and then finally rotational components of that. If we look at that one band over in the CO2 side, here pictured in red, it is overlapped and strongly blocked and redirected by the water vapor which drapes over it. This is the problem of using any of this information from satellites. It can't be seen. It is occluded from view and can't be used as part of the analysis. In the lower atmosphere, water molecules vastly outnumber carbon dioxide molecules and dominate this blocking effect and redirection of energy into the water molecules, its vibrations and its rotations. So this is the biggest thing that happens in CO2 in the atmosphere, but we're going to show what is wrong with using that as part of the theory. This is a comparison using satellite information. And what we're dealing with here is CO2. And here's that one large band at 14.9 to 15 microns. in the Earth glow. These ones are outside of the Earth glow. They are outside, all three of these for CO2. NASA and the European Space Agency use this small band here, just barely inside the solar glow component. Why? Because water vapor blocks this, or it is outside of the radiation bands which we're trying to use to analyze greenhouse gas retention of energy. They're using this one over here to comment on all of this. The blocking and redirection is a very major issue. So to be effective, we really need to consider what is happening where CO2 seems to be dominant. It is not, it's blocked. Earth radiates best to space in the water-free dry parts of the atmosphere. Deserts like this easily radiate and cool at night, irrespective of the quantity of CO2 that might be present. It's all dependent upon the water in that atmosphere as to whether it cools rapidly or not. Without water vapor, the atmosphere loses its energy to the cold void of space. CO2 can do nothing to store or retain atmospheric energy over the nighttime. Water vapor does that job. During the day, water vapor absorbs the highest energy parts of the solar spectrum. It is showing radiation heat loss and could be termed a desert finder, as it is intensely red in much of the desert regions of the Earth. The rest of the story is clouds, which is what's shown here, which block that radiant energy coming up from the Earth. And we also see large stretches of the ocean, which are also intense radiators, re-radiators of heat where the clouds are not present. This is a clear air view, or as clear as we can, in as cloudless skies as possible. But we'll see something else from 2018 that analyzes that better. The outgoing heat, the infrared radiation, long wavelength radiation, which is the Earth glow, and water vapor and CO2 is what we want to talk about in brief here. This is a contrasting kind of a slide. We're saying that water vapor acts over a very broad spectrum. It blocks and controls and redistributes the radiation. A water vapor's quantity increases logarithmically, directly along with temperature, and regulates temperature and vice versa. Water vapor, through its latent heat, stores and moves atmospheric energy and all other gases around. Daily and seasonal lags of peak temperature are excellent examples of water energy storage on Earth. Seasonal, North America, we have June as the longest day, but August is the warmest. And daily, we've got noon, which should be the hottest, but it isn't. It's 2 o'clock in the afternoon. Water is the dominant and only condensable gas in the Earth's atmosphere. Now, to contrast that, CO2 acts through radiation at the speed of light, does not store energy, and it vibrates it away. CO2 acts over a confined wavelength in packets, mostly at 15 microns, but is blocked there by water vapor. The abundance is not proportional to temperature. CO2 cannot store heat, only radiated away to space above the tropopause or to water vapor below that level. CO2 is not a condensable gas in the Earth's atmosphere. And as carbonic acid, CO2 is not properly understood. So we're going to try and elucidate on many of these points. So we got CO2, it's a really heavy gas, right? How are we going to move it into the upper atmosphere? Solubility is how we do that. The solubility of CO2 in water vapor is very high. So the water vapor is a very light gas, and it lifts it as it's rising, and it wants to rise. How do we know about what the CO2 is doing and where it is in the atmosphere? The rain. The pH of the rain has been changed, and we'll look at that. And it's made into a new substance between water and carbon dioxide. Plant origin and adaptation has involved a specific enzyme. It's called carbonic anhydrase. We'll discuss that in quite a bit of detail. The plant takes in these materials, that would be the carbonic acids, and it uses the anhydrase to break them down to yield water and carbon dioxide to promote its own photosynthesis. This would be the fertilizer for photosynthesis. So we've got to analyze all of these other new products now in the same way as the old ones have been. So, solubility in water vapor. CO2 is a polar molecule and becomes very soluble in water as temperature falls. As water vapor ascends, therefore, and temperature drops, the CO2 and the carbonic acid is taken up in the humid air and it rises with it. It's the weak carbonic acid diluted by the water vapor that we see as rain, which has a lowered pH. The water vapor is lightest at 18. Oxygen is 32, nitrogen is 28. CO2 is the heaviest at 44. As a pure gas, CO2 cannot float but accumulate in lows only. We don't see that. Only a bonding with light water vapor as carbonic acid can transport it to the plants to be used. This is the solubility curve. It's rising, the solubility of CO2 in water, as the temperature of that water is falling. The biology of the system. The CO2 bicarbonate carbonic acid is what we want to discuss here. The plants take up the CO2 not as a pure gas, but with water vapor as bicarbonate carbonic acid in the lower troposphere. Rainwater, cloud moisture and its pH reflects this. It moves from evaporation point at 7 pH. It moves to a slightly more acidic 5.6 before falling as precipitation. A unique and ancient enzyme, carbonic anhydrase, in the plant allows the CO2 in the water to be separated and used in the plant to conduct photosynthesis. This basic plant carbonic acid biology has been forgotten in all of the analysis of the current greenhouse theory. This oversight is a fundamental and serious error which models do not consider. This is that rainwater. CO2 in evaporated water makes it slightly, from seawater at 8, slightly acidic to pH 7, and then all the way up to 5.6 or so, where it rains out as carbonic acid. Carbonic anhydrase. It's a rapid-acting and high-volume catalyst, converting H2CO3 to water and carbon dioxide, which go on to become part of the photosynthetic system. This little guy here, the zinc in the middle, is the central element within this structure. These are proteins. These are enzymes. Now, there are other areas in animals and in bacteria that use a slightly different version of this, but all require it for life. In our human lungs, it's responsible for rebalancing the carbonic acid in our blood and the removal of the CO2 from our bloodstream. This is the beta version of it, which is used in plants. The plants do all of these things, of course, through their stoma, the closures or openings on their leaves. This formula down here is illustrating how this beta version sits in between carbon dioxide and water and hydrogen ions and bicarbonate ions over here. This is a part of the natural respiration cycle and transpiration cycle as well in plants. Under high altitude and colder conditions, carbonic acid cannot be easily delivered to the plant. This defines tree lines of latitude and on elevation of mountains on the earth. Tree growth rings show this moderation in the winter. Reduced growth based on lack of the delivery of CO2 and water in the winter. Nature would not have developed this catalyst if CO2 could be delivered directly as a pure gas. The whole process of pure CO2 induced global warming theory needs to be rethought. This is a complex diagram. It's got pH on the bottom here and the ratios of the various concentrations of CO2, HCO3 negative, and CO3 negative 2. We're going to deal with this portion here. This is where seawater would begin. This is where rainwater would end. It's all under really the umbrella of not CO2, but within the mid-range here, where carbonic acids and bicarbonates dominate. 100% CO2 dry ice. You've probably seen this demonstrated. There'll be dry ice in a bucket of water, warm water, and we get a fog, a bicarbonate fog, which comes off of this. So this is 100% CO2. It dissipates as carbonic acid, bicarbonate, in water vapor and rises with it from the bowl as a fog cloud. The cloud is trapped really by the warm air above it, like an inversion would be. The CO2 does not stay as a pure gas. When it is heated, the initial cold fog inversion of the bicarbonate holds together. But once it starts warming, it dissipates into the atmosphere to rise and to be carried as bicarbonate to plants. This is a rainfall analysis of the United States. These two lower portions here are what they focused their attention on. This was HCO3 negative and hydrogen ion concentration, pH, of the rainwater. And that's what they showed here with hydrogen ion concentrations and rainwater in millimeters. Their concluding statement is rather important to us. Regarding the carbonic acid or bicarbonate concentration map and precipitation amount, figure 4b, a significant inverse relationship has been observed, showing that an increase in precipitation amount decreases the amount of bicarbonate. And this is an indicator that CO2 does not have a prolonged greenhouse gas effect, since in the presence of hydrogen ions, it forms hydrogen carbonate, which is scavenged from the atmosphere in the form of carbonic acid. Carbonic acid, what does it look like in the radiation model that we were talking about earlier? These are the spectral absorption lines of carbonic acid, the forgotten component in the CO2 cycle. Let's transfer these onto some of the things we've looked at before. These are the peaks here. So there'll be 3 here and then one broad one back over here. Let's look at that. So this is the place we're going to transfer them into. If you remember, we had the CO2 and the water and the methane and oxygen here. We have the earth glow and the solar glow here. There's where carbonic acid fits, the blue ones at the bottom, the 3 peaks and then followed by the broad band here. What's going on with them? What do they contribute? What are they doing to this radiation cycle in the atmosphere? Here, they're blocked firmly by water. Beyond the thermal radiation windows, these areas where earth glow and solar glow intersect is where this sits, that broad band of carbonic acid. So carbonic acid does not attenuate the upgoing infrared radiation in any way. It doesn't contribute to a global warming. This is the graph of the climbing CO2 as measured in the north and south hemispheres. North is red, south is green over the years. This was done by the European Space Group. And this is the column of CO2 or parts per million that would have been climbing steadily through that time. Look at the difference between the southern hemisphere and the northern hemisphere. This is an average line, the black one in between. Quite a remarkable change between those on a CO2 basis. This is what it happens to look like when you blow it up a bit. This is the northern hemisphere CO2 concentration over here. And these are the years involved. We go through a fall, rise when all the leaves have died off, to a rising CO2, to a pause, a very strange pause in the spring. But that is the beginning of the cycle of absorbing of CO2, in this particular case, carbonic acid, from the atmosphere. But there's another rise, a second one, which happens up into the summer period. What is happening in there? This is important to resolve. It's what's happening near the poles. This process of CO2 blooming begins in the Northern Hemisphere winter. Back down here, we're dealing with November. And it pushes to the top of the troposphere as we go to January. So we have to go across here from November to January. It then rises as a wall up the edge of the tropopause. If you remember the shape, and that was the sudden step in the tropopause right here. This is using CO2 as a tracer of where energy is moving and air masses are moving. It's going from the polar areas up through there. But what's happening here? We have something else going on. In July, the northern hemispheric vegetation eats away at and diminishes the amount of CO2 in the atmosphere. That continues right through September, at which point we then revert again to the same seasonal up and down cycles. That's a CO2 tracer. These are the stations on the Earth that a fellow by the name of Howard Dewhurst is showing in this graphic. The discrepancy between the poles is what he's most interested in. But using CO2 as that tracer, he shows Barrow, Alaska, here in the blue with this huge up and down cycle versus what's happening here in the south of the equator areas. This would be in Tasmania and in Antarctica. The southern hemisphere doesn't show extreme spikes at all. This is the normal curve. This one from high up on the island of Hawaii at 4 kilometers at Mauna Loa, the observatory, looking at CO2, atmospheric CO2. It's being studied there by Scripps and a fellow by the name of Keeling over many years from the 1960s through till now. But what are we really looking at? What are we really measuring here at high altitude in light of what we just discussed in terms of carbonic acid? How do they get their pure carbon dioxide to analyze? It has to be pure. So what do they do? To accurately estimate the CO2 in the air samples, the process is described. It is separated and frozen to break it apart from water vapor that holds it and brought it there. Was it really carbonic acid? It seems that what we are measuring is likely carbonic acid and bicarbonate, not pure CO2. The greenhouse implications of this are very meaningful. Water vapor and energy. So if it isn't the CO2, is it the water vapor? Is that the thing that is managing to warm us more than what we had anticipated by some of these models that we have been talking about earlier? So under shortwave radiation from the sun, the solar glow, water vapor is dominant in absorbing of that incoming radiation. This has been underplayed in many of the models. Under long-wave radiation from the Earth, water vapor is also the most important greenhouse gas in the atmosphere. Outgoing heat radiated from the Earth's surface is absorbed by water vapor molecules in the troposphere. The water vapor molecules in turn re-radiate this heat in all directions. Some of it returns to the Earth's surface, and this is what we see as heat retention to allow us to not be in the cold of space, the cold equivalent of no atmosphere. Planets with condensable gases, all planets of this nature that we know about, have 3 phases: gas, liquid, and solid. That's what we have here on Earth. CO2 does not have those characteristics here in any way. These store latent heat for evaporation, condensation, and sublimation, let alone the heat that's been talked about earlier that's being stored in the ocean. Water vapor abundance rises logarithmically with temperature. This is the spectrum of absorption of water vapor, what it absorbs over the broad spectrum here of microns. This is a log scale, a little different than the last one, compressing a lot into it. We looked at 15 here before. We also see a large bulge here related to absorption in the ultraviolet. This is this area here, the V, is the visible spectrum. This is why water vapor is invisible to us. It's the most energetic, but doesn't absorb as much within the visible wavelengths. Water content in the air, pounds of water vapor, rise dramatically with temperature, depending upon the relative humidity. So relative humidity is something we won't really dwell on too much, but what we're dealing with is a logarithmic rise of water within the air. The amount of water being held in the air is dramatically rising, and therefore that changes everything about the equation of how water vapor acts to preserve and to hold energy in the atmosphere and rain it back down to the earth. Abundance of water vapor thus determines the absorption rate of that energy. This is a satellite study. It was done in 2018, or compiled then, but done over many years before that from data that was accumulated. It looked at the outgoing radiation, and it's all satellite data, it's multi-year, and it was done in clear skies. So that was meaning there were no clouds to actually inhibit what was being looked at in any way. The color intensity here within this band is how many data points there were to look at. What the conclusion is from this of outgoing radiation in watts per meter squared over temperature in degrees Kelvin is showing a linear relationship. This was unanticipated. This was not expected. It was supposed to be a hyperbolic curve here that was anticipated. What was going on here? According to the authors, the log curve of humidity minus the log curve of black body radiation results in a linear trend. The outgoing long wave radiation responds directly, linearly to temperature. Thus, thermal radiation from the Earth is controlled by water vapor, not CO2. There is no radiation energy fingerprint being detected directly from CO2 molecules in this satellite data, only water vapor radiant energy. Weather balloons and work of that sort have corroborated this from 1980 to 2010. And this one, at various parts of the upper troposphere, we're dealing with these heights in kilometers in different colors. The troposphere is about here in elevation generally, and the stratosphere higher slightly. These show the parts per million of water. It's climbing. It's climbing in steps. It's jagged. It's not uniform. It's stacked, and all of the elevations are responding together. It's pulsating in stages, rising and falling, and not reacting as we might have expected if it were due to unevenly distributed gas. Here's a continuation of that to add some more years from 2010 through to 18, showing the same kind of progression at all levels. Here's a conclusion by Dan in 2021. He's looked at the water vapor readings that we just looked at. He's shown them here as a black line, calling it total precipitable water. In that, he has actually gone ahead and then compared that to, at the top, the temperature as many different groups have estimated it around the world. These are the groups that did it, NOAA and HADSET and et cetera, et cetera. So all of these are showing variations, some of them more extreme than others. all of them in the extreme areas are showing a coincidence, a remarkable coincidence with the total precipitable water as we've been looking at. This is the carbon dioxide rising trend that we looked at from the Keeling work carried right through to 2019. It is not varying in that same sense. It is not correlative in the same sense as what we're getting here between water vapor. Well, why? What's going on? What's special about that? Well, Dan has a feeling that we're also being dominated by excess water that's being put into the upper atmosphere. That water can be sourced, he feels, from this irrigation water. Taking water and putting it into irrigation worldwide from 1950 or so has created a tremendous bloom in the amount of water vapor available to the atmosphere, the total precipitable water. I want to talk about CO2 now for a little bit again. What is the real retention time of CO2 in the atmosphere? This is a strange diagram to put up, but what it is showing is a big open air experiment that was unintended using carbon and carbon-14 in this particular case. What did it tell us about carbon? This is the atomic spike that resulted from all of those explosions. This is when the test ban treaty kicked into place and stopped all further open air testing. Rapidly, the curve plunged, as a normal decay curve will within a natural system. We learned several things from these lessons about CO2. The abundance of CO2 determines the absorption rate and falls in a logarithmic decline curve toward a natural base level. The residence time of CO2 in the atmosphere is far shorter than any model builders and IPCC have tried to convince the public of. These are the two models. This would be what the IPCC uses, the burn model in blue. These are what those atomic results show, the carbon-14 results. The IPCC residence time as a result in the atmosphere is shown as a red bar and grossly exaggerates what is shown by many other researchers and many other studies here in the black bars. Why would the IPCC make this assumption in face of all the rest of this data? I don't have the answer. We're going to look now at a model which is called MODTRAN. It's a way of looking at the CO2 and, in this particular case, also the O3 and the water vapor and how they influence the radiation that's coming back up from the Earth's surface, the stuff that's supposed to be trapped. It is a way of calculating that, which is model-based. If we look at the difference here that's shown on the bottom, we may or may not be able to see the difference between the lines. The red line is 300 ppm CO2. The blue line is 600 ppm. The difference between those in watts per square meter is very small. Very small, especially in terms of the error limits, which we had discussed earlier, which exist in any model. And all of these models have very large error limits within them and assumptions. Let's take a look at the inverted image or an equivalent image. This is a real one from the mid-Pacific area. We want to see how O3 and CO2 are and where they come from. These lines, the ones that were on the previous one, are now inverted here. These are the temperatures of the altitude or of the atmosphere as we rise in altitude and cool. So this is near the Earth's surface here at this temperature. This slide is actually, of course, a spectrographic view, and so it's not a model. And what we're going to do is look at where we are. So CO2 at 15 microns is what we'll focus on first. That's in this area right here. Now, what's happening is that it also is part of an equivalent to this particular area here, which is low temperature. We're at negative 53 degrees Celsius at the top of the troposphere. This is 18 kilometers above the tropical Pacific equator in this view. And the CO2 is a radiator of energy very high up in the atmosphere, but is much less significant at all in the lower parts of the troposphere. We have no measurable effect below 4 to 5 kilometers. We've discussed that in terms of other reasons for that, being in a different waveband completely related to carbonic acid. But in this particular case, we are getting CO2 and its effects showing up higher up. The water, and it's across the whole spectrum, we're getting it at a -3 and -3 here, and also closer to ground at about +14. So it dominates the whole spectrum except for those other little peaks which are showing up. So it's at a freezing level at -3, as you'd expect. And so that's where a lot of it is dropping out and not as very effective. The O3 is acting in the warm inversion zone of the stratosphere, which is at about +7. Higher up, where the warming from the creation of ozone in the upper atmosphere takes place because of bombardment by ultraviolet light. So those are the reasons, but are we really clear on why and how CO2 or O3 really influence the ground level temperatures and our ground level conditions? This is a continuous column, but it isn't something that's clear within a lot of the reasoning or people's understanding of how CO2 especially influences climate. So a profile view, CO2 does not act below 6 kilometers. So here's kind of a profile view of that. Here's Mauna Loa and here's Everest. Here's the CO2, maybe beginning its ability to act as a greenhouse gas in the upper atmosphere here, but dominantly looking at its biggest area way up high at -53 degrees C. These are the carbonic acid components. The ice of this nature is a speculation as to whether we also have carbonic acid ice. These are ice clouds, of course, related to the water cycle, which goes from 14, we said, to -3. The ozone, here it is, sitting up anomalously at +7. Reheating, as you remember, because we have that thermal inversion. We cool down and then we heat up again. The only significant radiant power in theory attributed to CO2 comes in the first 0 to 280 parts per million over in here, moving from this point down to this point. Of the total theoretical power curve shown, 86% occurs in the first 280 parts per million. Glaciation, at times of glaciation, the CO2 in the ice core, if you remember, is sitting in about this area here at 180. The real form of CO2 as carbonic acid in the lower atmosphere is not being shown in this model. The CO2 is involved as a pure gas only here. Higher up in the atmosphere is the place it can act. And the ppm at that level should be thinner. This is a model built on, ppm sliding across the top here. 800, 600, 400, 200. Where is the CO2 going to be on a ppm basis in that upper atmosphere? And how will it influence? As with CO2 saturation in the previous slide, water vapor also saturates, as shown in this Motran model as well. This compares the two of them. This is the 30 watts per meter squared that we saw from the last one with CO2, theoretically. And this one is where water vapor is theoretically in this model. This is a factor of 3 to 4 times, and certainly shows that water dominates. So I'd like to summarize. We've covered the Holocene, the last 11,000 years. The temperature and the CO2 are not linked there. CO2 is not driving heating in the Holocene in any regard. Solar activity is linked to temperature. Temperature is linked to ocean currents and water vapor. The ITCZ moves north or south seasonally and climatically with tilt of the Earth. Models have large air limits. They poorly define the small energy imbalances as a result. They exclude major areas of significant interest in climate analysis: the ocean energy storage system and clouds. Recent work in solar activity drives water vapor absorption. The solar activity is what seems to be driving our current water vapor, as we saw, and energy within the system, not greenhouse gases per se, excepting water vapor. Atmospheric analysis of carbonic acid and products that are not CO2 needs to be done. We've illustrated this by rain, the pH of the rain. We've shown it because there's an ancient catalyst which has existed forever, which says that plants always get their CO2 this way, not from some pure gas in the atmosphere. Water vapor dominates both carbonic acid and CO2 radiation bands. We showed that. And so therefore, we should be really concentrating more of our effort away from the carbonic acid and the CO2, except where it promotes life. And we'll get into that in part 3. CO2 appears to re-radiate and cool the upper troposphere. Is something that we are just starting to realize. What are its influences lower down? Negligible. Thanks a lot. Bye.
That is the end of the second part of the lecture on paleoclimatology. Part 3 will add to the story by including clouds, ozone, and biosystems.